right, so we'll get started with a little bit of an algebra review. I always say in calculus that algebra is pretty important, so that's why we take a little bit of time in the beginning to review some things. So first thing is the idea of a function. That's a rule typically for us an equation that assigns to each element in one set that we call the domain to one and only one or exactly one element in a second set that's called the range. Okay, so that's our definition. The set of all those first elements are the domain. Domain is also the set of all the inputs for the function. And all the second elements will be the range, and the range will be the set of all the outputs. Hopefully you remember the vertical line test, which says if no vertical line crosses a graph in more than one point, then that graph is a function. All right. So to begin with, all right, so to begin with, we're going to evaluate some functions, or which just involves substituting in a function. So when you see f of x, that's your function notation, and f of -1, what does that mean? What does that tell you to do? Tells you to substitute the number in parentheses for x, right? So we call this finding a function value and that involves substituting the number, the number, or as you look right down at part B, it doesn't have to be a number. It could be an expression, a variable. So you substitute the number or the expression for x in the function rule. Okay. So when we substitute -1 in the function, then we follow the order of operations. So when I square -1, I get +1. The -2 times -1 becomes +2, and that's just 3 + 2, which is 5. Sometimes we want to substitute, like I said, an expression into a function. So just as I mentioned, we're going to take that x plus h. Let me add something here. Yeah, so we substitute the number or expression that's in the parentheses for x, or whatever variable. It doesn't have to be x. So basically up here where that x is, that's where I'm substituting. All right, so I'm putting x plus h in place of x up in that function rule, and that's the first step. Now in part A, what I said, follow the order of operations. So the first operation that will need to be done is squaring. All right, so I'm going to say by the order of operations, first thing I'll do is square. Most people, I would say, would do that squaring by FOIL. So I'm going to take a minute and write that as x plus h times x plus h. Keep in mind that when I square x plus h, that's how I square it. I don't go in and square the x and square the h. There are actually four products involved with that. With the x plus h squared. So by FOIL, I get x squared. The outer product is hx. The inner product is hx. And the last, or the product of the last terms will be h squared. All right, so that's what I'm saying, that's squaring by FOIL. Second step is to remove the parentheses by multiplying. Okay. So it's also called the distributive property. So I'm multiplying inside the first set of parentheses by 3. Now this is where you want to be careful because there's a minus 2 that's in front of the next set of parentheses. So distributing or multiplying by -2 gives me -2x minus 2h. All right. And then the third step will be to combine any like terms. So in this case, the only terms that are like are the ones that I just underlined. That there's a 3hx and another 3hx. I combine those by combining the coefficients, the 3's. Oops. All right. And that's about all I can do with that. All right. So let me just say again, as always, if you have a question, just unmute yourself and speak up, and I'll answer your question. Any questions on that one? Okay, if not. Okay, now we're looking at some graphs to see if they represent functions. This is the vertical line test that I mentioned a minute ago. So remember what it said, if there's any vertical line that crosses the graph in more than one point, then it's not a function. So for part A, if you can find a vertical line there, you need to let me know where it is, but because there's not one. There's no vertical line that would ever cross the graph in more than one point. Therefore, this one is a function. All right. The graph over in part D is not a function. It only takes one case, but there are many vertical lines that would cross that graph in more than one point. So because this thing does, the vertical line that I just drew does cross the graph in more than one point, this is not a function. All right. Vertical line test. Any questions on that? Oh no. Oh. Okay, I believe what's going on here. It's not recognizing some of my fonts. Oh. All right, so probably gonna have to go. No. Okay. I know what it is, but I don't really know how to fix it at this point in time. Let me think. I'm really confused. All right, so sorry about that, but I have a quick fix. I'm going over to the PDF version, which I don't like as well, but let's see. At least you can see the symbols that didn't show up before. All right, so next we're talking about domain of a function. So remember the domain. Let's see how this is. Let's see. Okay, I can't write on it. All right. Remember the domain of a function is the set of all inputs. Typically, you know, in a graphing situation, we're looking at x's, but it doesn't have to be x. It's just whatever the input variable is. So I like to break it down into the different types of functions. All right, a polynomial function. The domain is all real numbers. And as we go through the different things that we learn in calculus, what you'll see is everything that we do, polynomial function is the easiest case. And this is actually one of the reasons, because the domain is all real numbers. Actually, I might want to take a minute. What do we mean by polynomial function? Because maybe you've forgotten what that is. Let me take a minute and say, okay, if something is a polynomial, let's see if I can get rid of that. Ooh. Ooh. Oh, that's just great. Okay, I just got rid of all my ink. So, all right, I'll fix that. Okay, polynomial in general, the variables have positive integer exponents. And what that means, if a positive integer exponents, what that means also is that there are no variables in the denominator. And there are no variables under a radical. Okay. And again, as you'll see throughout the course, those types of functions are not the simplest case, starting right away with the domain. All right, so domain, I have a little note here that got erased. That's the set of all the inputs for the x's. All right, so for domain, all real numbers. Let me also say the domain, these are the numbers that give defined outputs. Okay, so once we get to a square root function, for a square root function, and notice I call that an even root function. So that would be like a 4th root or a 6th root. We typically don't see that. Probably won't see anything other than just a square root. But for that type of function, we can only put numbers under the radical that are non-negative, because square roots of negative numbers are defined, but they're not defined in the real number system. And we will only be working in the real number system. All right. So for the domain of a square root function, you've got to find all the numbers that make the expression under the radical, which is called the radicand, non-negative. All right. And this is how you do that. You set the radicand greater than or equal to 0 and solve for x. I'll tell you what, why don't we go ahead and hop into the examples, and we'll talk about those as we go along. Okay, when you're given the graph of a function, and I'm pretty sure that's an open circle down there at the bottom left hand of the graph, okay? So when you're given a graph, you're basically reading the domain and range from the picture of the graph, okay? So looking at the domain, I like to say I'm reading the graph from left to right. All right, reading it from left to right, because these are the x's. So my x's start right here at -2, and they stop at +2. So basically the x's are going from -2 to +2, but what's happening specifically at -2 and +2? So the open and the closed circles tell me something different. All right. On a graph, an open circle tells me that the point is not included in the graph or in the function. So an open circle indicates that point is not included. Okay, and a closed circle indicates that it is included. When we start talking about calculus, which we'll do next week, we start talking about limits, this concept is pretty important. All right, so what's happening at the -2, where x is -2, because of the open circle, we do not include -2 in the domain. All right, so here's one way that I could write the domain if I wanted to. All right, that says x is strictly greater than -2 and less than or equal to +2. And that's one way to write that set of numbers. Typically in a calculus class, even in an algebra class, interval, we want to write the answer in what's known as interval notation. And the interval notation that goes along with this set looks like what I just wrote. Okay, so that's just another way to indicate the numbers that are greater than -2 but less than or equal to +2. All right, Wish I could change colors on here, but I haven't figured that out. All right, as far as the range, so the range of a graph is read from bottom to top. Read the graph from bottom to top. All right, so let me see, let me add this to my picture. The first set of arrows that I wrote, those are where the x's start and where the x's stop. Now I'm looking at where the y starts, and that's at -10, and then the y stops up there at 6. All right, so what I would say for my range, the y values are greater than -10, but less than or equal to 6. All right, and again, the open circle tells me that the y value of that point is not included. The closed circle at the top tells me that the y value of that point is included. All right, and then interval notation looks like this: -10, comma 6. Again, the parenthesis and the interval notation goes along with the strictly less than symbol in the inequality notation, and the bracket goes along with the less than or equal to symbol in the inequality notation. Okay, so are there any questions on that one? Okay. All right, going to number 4. Find the domain and range of each function. And actually, let's just find the domain, because the range will take a little more work, and right now I'm really just interested in the domain. All right, so looking at the function in part A, if you look at the exponents on the variables, remember there's an understood 1 right there. So the exponents on the variables are non-negative integers. Maybe I should just take a minute. What are non-negative integers? That would be 0, 1, 2, 3, and so on. Okay. All those are positive integers except for 0, so that's why we say it's non-negative. 0 is non-negative. All right, so because all of those exponents are non-negative integers, I would classify this as a polynomial function. And a polynomial function will always have for its domain the set of all real numbers. Okay? There are several ways to write that. One way is to put this kind of fancy looking R to stand for all real numbers. As an interval, this is how we symbolize all real numbers. We say, okay, we want all numbers from -infinity to positive infinity. That's all of them. Okay, so that is interval notation for all real numbers. Okay. Now looking over at the function in part B, this is a square root function. And remember that we can only put numbers in for x that make what's under the radical non-negative. In other words, what's under the radical can't be negative. All right. So if you were to go back and look at the instructions or the rule up here in part 2, specifically this part, to find the domain, you take the radicand, which is just simply the expression under the radical. You set that greater than or equal to 0 and solve for x. All right. So to find the domain of this one, I'm going to take x minus 1, set it greater than or equal to 0, and solve for x. And that's pretty easy to do. I just add 1 to both sides. And I get x is greater than or equal to 1. And that's actually, you know, one way to write the domain. We're saying, hey, x has to be greater than or equal to 1. The interval notation that goes along with x greater than or equal to 1, that's a bracket, looks like that. That's another way to write all numbers, is saying, hey, start at 1 and include the 1, and then continue forever to infinity. All right. So let me know if you have a question. Does anyone have a question so far? No? All right. Well, stop me if you do. Okay, the next problem, this is what we call a rational function. So I'm sorry to say, these will be the kind that you don't like. The rational function has a variable in the denominator, and that is not the easiest case of everything we do. In fact, it's probably the hardest case of everything we do. The reason for that is, if you remember, division by 0 is undefined. So we're always watching out for numbers that might cause that to happen. Okay, so the way that we get the domain of a rational function is to take the denominator, set it equal to 0, solve for x, and then throw those numbers out. Those are the numbers we can't use, because they are in fact the numbers that make the function equal to 0. All right. So looking at problem 5a, looking for the domain. So remember, the rule here is to set the denominator equal to 0 and throw out those numbers. So the denominator is x minus 5. I add 5 to both sides, I get x equals 5. In fact, you might even do it this way. Well, actually, that's what I set up at the top. X minus 5 cannot equal 0. Therefore, x cannot equal 5. And I'm trying to remember, I think this is how you're going to see your answers written. If we write that in interval notation, it's more complicated. I'll double check and take a look at that for homework, but that's how I would prefer you to write the answer, because that's pretty specific. Hey, we can use any number we want except 5. And that's a good way to write that. Okay. Same thing for part B. I'll take that x squared minus 4, but it can't equal 0. Now, let me just remind you of some terminology. The equation over in part A that I solved, that's called a linear equation. My A's are looking funny. This equation in part B, this is a quadratic equation. And the methods for solving these are different. Linear equations, pretty straightforward. Get the variable by itself. For a quadratic equation, well, there are a couple of ways to solve this. I would probably use the square root method, which says I'm going to add the 4 to both sides, and I need that to go away. The square root method says, hey, you can take the square root of both sides of an equation, but you have to use a plus or minus symbol because there are always going to be two numbers that you can square to get a number. For example, when I follow through with this, I get x cannot equal plus or minus 2. Because how do I get, what number can I square and get 4? Well, I can square 2 and get 4, and I can also square -2 and get 4. All right. So for my domain, I'll just use a D. Let's put that over here too. For the domain, I'm going to say all real numbers, but x cannot equal 2 or -2. All right. Let's circle my answer. Okay, so far so good. I can't see y'all, so I don't know. Could be over there sleeping, but if you have, well, thank you for a little bit of interaction there, Allison. I like that. She's not. And if you are sleeping, remember that I'll post this video. I figured out, how to do that. I'm uploading them to YouTube, and then I'll post the link to that on D2L. All right.
I have a question.
Yes.
Do you have this PowerPoint where we're able to print it off?
So it's not a PowerPoint. It is, so that's a good question. Let me stop for a minute and see if I can get to my D2L. That's on title. All right, let me do some let me go over here and see if I can get to how to log out of that. Oh, gosh. Trying to get to your D2L page. Okay. We're working on this. Okay. All right, do you see, here's your home page in D2L.
Yes, ma'am.
Okay. Over on the table of contents, this is where I'll put a link for the Zoom videos. But over here under test 1 materials, I'm working, these are the notes that I'm using. Here's section 1.1. Actually, that's not the section we're doing. And that might be why you're asking. Oh, here it is. I'm sorry. It's the math. This is it. The Math 1232 Algebra Review.
All right.
You got it?
Yes, ma'am. Thank you.
Okay. Sorry, I should have mentioned that. Yeah,
No,
that's all right. Okay. Yeah, they're all up there. All the I call them my class notes. Typically, my students will print those, and before class, so you can print them or just follow along, whatever you want to do. And let me also say that at the end of this section, so I'll post the video. I'll save what I'm writing and just post that as a document. So if you just want to look at the document and not have to listen to me talking again, you'll have that as well. All right. Okay, piecewise defined functions are next. Let me take a look, see what else I've got to do here. All right, it should be okay. All right, so piecewise defined functions are just that. They're functions that are defined in pieces for different intervals of the domain. Here's an example of what one looks like. Whew. So this is asking us to graph the function. That's all I'm asked to do. Okay. So for graphing, I'm going to highly recommend that we use our graphing calculators. Just speeds things up and makes things a little bit easier for all of us. So I'm going to go ahead and just show you how you would type this in, your TI-84. If you're using Zoom, I don't know how, let's see if I can get to the chat. How do I get to the chat? If you're using Zoom, would you either just unmute yourself and say yes, or just go ahead and do that this time? Is anyone using, I'm sorry, I don't know what I said. I meant Desmos. Is anyone using Desmos?
Yes, ma'am.
Okay. So I'm going to make myself a note for Desmos. I'll do a different, I don't know if I can do all that in one recording session here. So I'll probably do a separate little talk on Desmos for this, all right? Because it is different. Was that Allison?
Yes, ma'am.
Have you used it before?
Yes, ma'am, I have.
Okay, I didn't remember. Okay, so you may know how to do this.
Okay.
In Desmos, you have to enter this as two separate functions. And I'm not sure what just happened there. All right, so in my TI-84, I'm going to go to the function screen. Well, actually, you have to enter those two different functions in there too. The function, the Y editor, I'll show you on the calculator in a second. But this is how I'm going to enter it. It looks almost exactly the same as it does on paper. In place of the if, you're using the division symbol. When you use that, it brings up that flash, okay? All right, see if my calculator is still with me here. All right, okay. All right, so I'm clicking the y equals key and clearing what's in there. Now I have to remind myself. It's 5 minus x. So in parentheses, 5 minus x, close the parentheses, the division symbol, open parentheses again, and then I wanted x, oh, my memory's going, x less than or equal to -2. All right, the any less than or equal to is an inequality symbol. And those are located under the test menu. I don't know if you can see my cursor moving around, but test is right above the math key. So to get there, I press second and the math key, and then you can either arrow down or just type 6. And then it's -2. Oh, I just made a big boo-boo. Okay, right here, that should be the negative symbol, not the subtraction symbol. I don't know how I did that. I'm out of practice. So if you notice the difference, we've got 5 subtract x, but then x is less than or equal to -2. So the TI distinguishes between the subtraction symbol and the negation symbol. And it'll probably give you an error if you mix those up. Okay, then for the other function, the second piece, it's going to be x squared minus 1. I think someone's not muted. If y'all be sure you're all muted. It might interfere with sound. Okay, so x squared minus 1, parentheses, division symbol, open parentheses, and now I want x greater than -2. Back to the test menu, and I'm just going to press 3 rather than arrow down, and then -2. All right, so that's what it looks like on your screen. Typically what I do is post these, put the screens in as well, but I don't think I can do that with my PDF version, so I'll have to fix up the Word document later. All right, there it is. I'm going to check the window. My window, that's the standard window, but if yours is in a different window, you want Zoom 6, standard window. And again, once you press the Zoom key, you can just type 6 or arrow down and press 6, and there's your graph. Now, so your graph is pretty good. Your calculator is pretty good. It doesn't show what's happening at the place where the pieces meet, which is at -2. So I'm pretty sure, like I said, I'm not going to be able to get this in there, but I'm going to attempt. Add text and images. Oh, okay. I stand corrected. All right, do you guys see the TI screen?
Yes, ma'am.
Okay.
Yes, ma'am.
Oh, I hear a person. Let me save this before it goes crazy. All right, so that's good. Covering up some other stuff. Let me maybe see if I can move this guy over here. There we go. Okay, so there's your graph. um, I want to stop editing, but I don't know how to do that. Oh, goodness. I want to stop editing, please. I'm sorry, guys. PDFs, I don't use those that much, so. Okay, let's just see what's gonna happen. I'm gonna try here to, no. Ooh. Huh. I don't want to do that, or I don't want to do that. Da-da-da-da. This is why I like to use the Word document if I can, because now I don't know how to get out of the editing. Wow. Okay, this is a mess. I'm gonna need to go back and fix it up. So I'm gonna go. Oh man.
I don't know if this would help, but maybe try hitting the edit button again.
Try doing what?
Hitting the edit button again, because it's highlighted blue. I don't know if that would help.
Okay. I thought I tried. Right. I thought I did that. I'm clicking it and it's not doing anything. I even clicked more, and so I don't see it there. Add sticky note. Ah, okay. I clicked it. I clicked the arrow button, but I don't know. No, that's okay. It's okay. I'm sorry, guys. All right. Wow. Okay. For the blue piece of the graph, I'm putting a closed circle on the end, which goes along with the less than. That's because of this equal bar right here. And then I'm putting an open circle on the red piece, and that's because there's not an equal bar with that piece of the function. All right, so let me add this, and the equal bar with an inequality. Oh my goodness. Okay, now my computer is gonna go nuts. Oh jeez. Okay, I'm sorry. This thing is just nuts. All right, I think I'm back. All right, an equal bar with an inequality tells you put closed circle at the point with no equal bar, put an open circle at the point, if that makes sense. Okay, so like I said, the blue line represents the first piece of the function. So where x is -2, I put a closed circle because of the equal bar. Let's see what's going on here. Don't be doing this now. Okay, let me move on. I think I've upset it by putting that screenshot in there. Okay, So next will be a little bit of review on lines, equations of lines, and so forth. So there are several forms of equations of lines. First one is the slope-intercept form, y equals mx plus b, right there. That's when you know the slope and the y-intercept, or if you have an equation in that form, you can read the slope and the y-intercept. Point slope form, that's the form that we use most of the time to write the equation of a line. And we do that in calculus a good bit, so we want to review that, although there's actually a cool way to do that on your calculator that I'll talk about when we get there. Okay, so for example 7, notice the information that I have. I'm given a point and the slope. Remember, m is for slope. So I basically go up and substitute from the point. That's my x sub 1 and my y sub 1, and the slope, like I said, that's m. I substitute directly into that form, which I'll write here. All right, I'm putting, in place of y1, I'm putting 8. Negative 2/3 for m. Negative 3 for x sub 1. Notice there, with this form, you have to be really careful with the subtraction and the formula and a negative number. All right, I'm going to, I think what I'll do is go ahead and get that double negative and make that a plus 3. Then I'm going to distribute the negative 2/3. So negative 2/3 x, and negative 2/3 times positive 3 is negative 2, which you can put that in your calculator if you need to. And then to finish it up, I'll add 8 to both sides, which gives me the way that I was asked to write the answer. It said give the equation in slope-intercept form, and what I've just circled, that's slope-intercept form. Okay, that's typically how we're going to write our equations. Okay, and then problems 8 and 9 deal with what I call the special cases, horizontal and vertical lines, which I'll leave that information up at the top of the screen. So a horizontal line, if you look up the top of my screen, it says the equation is y equals c, where c is the y coordinate of any point on the line. Another way you could write that is y equals y sub 1. So in problem 8, my y sub 1 is negative 3. So the equation of my line is simply y equals negative 3. It's basically that straightforward. Okay. And then for a vertical line, remember the slope of a vertical line is undefined. So the equation of a vertical line is x equals the x coordinate of any point on the line. Oh my gosh. My computer is not happy with me. So my x coordinate is 5. That's my x sub 1. So the equation, and I forgot to mention, because I'm told that the slope is undefined, I know that's a vertical line. So the equation of my line is x equals 5. Okay, any question on that, on any of those? How's my time? Okay, I got 15 minutes, so we're pretty good, I think. Yeah, the last few things we do, because your textbook talks about these items in their algebra review, and because our course is primarily geared towards applications from the business world, we want to go ahead and talk about some business topics: cost, revenue, and profit. A cost function is comprised of two costs. There's the variable cost and the fixed cost. Fixed cost is what it sounds like. It's fixed. It stays the same no matter how many units are produced. But variable cost is related to the number of units produced, okay? Fixed cost could be like rent, utility bills, salaries. Variable cost, suppose you're making t-shirts, so every time you run the machine to print a t-shirt, that costs something. That would be the variable cost. All right. All right. So the variable cost, there's a little formula right here. It's the cost per unit times the number of units. X typically stands for the number of units that will be produced or sold. The revenue, that's how much money you're bringing in. That's the selling price per unit times the number of units. And then the profit, let me back up. We refer to the cost function as C of X. Cost is a function of X. And the revenue is R of X. And then the profit, which is why most companies are in business, is the difference between the revenue and the cost. So it's revenue minus cost, okay? Break even occurs when cost and revenue are equal. Another way to look at that is when the profit is equal to 0. Typically, we're interested in the profit starts being positive, and that's typically after break even. All right, so we've got an example. A computer manufacturer has a fixed cost of $3,300 and a variable cost of $85 for each computer produced. The computers sell for $385, and we want to write some equations. So notice X is the number of computers that are produced and sold. The first thing we want to do is write the cost function. So let me just remind you, that's the variable cost plus the fixed cost. We use C of X for our function notation. All right, variable cost is $85 for each computer produced. So mathematically, we write 85 times X, and then the fixed cost is just a number, 3,300. That's your cost function. All right, the revenue function, I won't rewrite the formulas up above. That's the selling price per unit times the number of units. So the computers sell for $385 each. Multiply that by the number of units, which is X, and that's your revenue function. So those are my cost and revenue. I'm listening. Okay, that wasn't meant for me. All right, now for profit. The profit is the revenue minus the cost. So now I just do some algebra. I'll put P of X, take the revenue function that I just formed and subtract all of the cost function. All right, so the parentheses here are pretty important because you're subtracting, like I said, all of the cost function, which has two pieces. So I now have to go in and distribute negative. Okay, so let's see, parentheses here are important. Distribute the negative. And then combine like terms, which are the x's. $385 minus 85 is 300. And there's my profit function. Okay, the next thing says find the cost, revenue, and profit on the sale of $300. Okay, so that means I said $300, 300 computers. So I want the cost for 300, the revenue for 300, and the profit for 300. And that's just a matter of substituting in the functions that I created. So for the cost, that's 85 times 300 plus 3,300. I'm gonna bring up my calculator. And that gives me $28,800. For the revenue, 385 times 300 is 115. So they're gonna make some money here. 115,500. And then if I substitute 300 into my profit function, I should get the difference between the two numbers that I just found, which is 86,700. Nice little profit there. Okay. Okay, and then finally find the break-even value. So there are two ways to do that. You can either set revenue and cost equal, or you can set profit equal to 0. That's what I'm gonna do. Reminding myself the profit function is, so the profit function was 300x minus 3,300. I'm gonna add 3,300 to both sides. And then divide by 300. And it's 11. 3,300 divided by 300 is 11. Okay, so that means after the sale of 11 computers, they're making a profit. At 11 computers, they break even. Okay. Stop me if you have a question. The last topic for this stuff is supply and demand and market equilibrium. So supply and demand, consumers, you know, there's something for sale. The consumers demand it and the company supplies it, or producer supplies it. And they're related. The two things are related. And they're related by the unit price and then either the quantity demanded or quantity supplied. All right. Just for your information, in the middle of this box says that the law of demand tells us that the quantity demanded will increase as the price decreases. Should make sense. And then as the price of a product increases, the quantity, wait a minute. Something right there. The law of supply states quantity supplied will increase as the price, I think that should be decreases. I don't know. That doesn't sound right, but I'll check that. Okay, then market equilibrium occurs when the quantity demanded is equal to the quantity supplied. And then we have what's known as equilibrium price and equilibrium quantity. All right. So in the next example, we have, I'm not going to do that one. We have a demand function and a supply function. Q represents the number of units produced and X is the price. So keep that in mind. All right, find the equilibrium point. So again, we just set the supply and demand equal to each other. And since both equations are solved for Q, we just put the 5800 minus 60x equal to the other function 600 plus 40x and solve that for x. Now what I would do, I like to keep my variable term positive, so I would probably add the 60x to both sides to keep the variable positive. Then I would subtract 600 from both sides and then divide both sides by 100. Divide both sides by 100 gives me x equals 52. So that's going to be the equilibrium price because x is the price in dollars. It also asks us to find the equilibrium quantity. So what I'm going to do here is take either equation I like. I kind of like the supply one better. It's a little easier to work with. And I'm going to substitute the 52 for x in either equation that I like. So like I said, I like the easier one. I'm going to take 600 plus 40x and substitute the 52 and calculate that. And I get 2680. That is the equilibrium quantity. Okay. All right, sound good?
Yes,
I'm
ma'am.
not, okay, good. I'm not gonna worry about number 12. Those are, I'm not gonna give you any like that, so we just stick to these simple kinds of functions. Any question on that one or anything that I've said? Um, okay. Cool. All right, let me stop the recording. I can figure out how to do that. Stop recording.